lecturer, Mining Engineering Division, University College of Engineering, Kagti University, Kottagudem, and other colleague, Honorary Secretary, Sri B. Srikant Garu, and Joint Secretary, Sri Karun Kumar Garu, and other committee members of IEI Kottagudem Local Center, distinguished guests, colleagues, participants, and friends. This is Rama Mohan, Chairman IEI Kottagudem Local Center. It gives me great pleasure to welcome you all to the session on the application of numerical modeling in mining. We are gathered here today to explore one of the most powerful and transformative tool available in the modern mining industry, that is numerical modeling. As the mining sector evolves to meet growing global demands while adhering to stricter safety, environmental, and economic standards, the role of predictive modeling has become more critical than ever. Numerical methods allow us to simulate complex geological conditions, evaluate mine stability, design support systems, and optimize resource extraction with a level of precision that was unthinkable just a few decades ago. Today, we will delve into how numerical modeling is being applied across various stages of mining, whether in underground or surface operations, geomechanical assessments, or the design of efficient mine layouts. This topic brings together engineers, geoscientists, researchers, and data specialists in a shared effort to make mining not only more productive, but also safer and more sustainable. I would like to thank all of you being here. Your presence is a testament to the growing interest and importance of computational tools in mining engineering. I also extend warm welcome to our panelists, moderators, and other members, experts who are sharing their insights, case studies, and innovations in this field. Let us make the most of today's discussion and collaborations. I encourage each of you to engage actively, ask questions, and share your own experiences. Just I would like to brief you about the Institution of Engineers India, commonly referred as IEI. It is a professional body that represents engineers across various disciplines in India. It is founded in 1920 and incorporated in 1935, headquarters in Kolkata. The primary aim of the institution is to promote the development of engineering profession, assist in the advancement of technology, and provide a platform for professional growth, knowledge exchange, and networking. IA works to enhance the standards of engineering education, ethics, and practices, while also focusing on fostering the growth of the engineering community in India. It conducts various conferences, seminars, and technical events, and offers memberships for the engineers in fields such as civil, mechanical, electrical, and more. The institution is also involved in promoting engineering research, collaborating with academic institutions, and providing certification for engineers. Regarding Kottagudem Center, is one of the region chapters of IEI located in Kottagudem and serve as the hub for engineers in the region, facilitating various professional activities including technical lecturers, workshops, training programs, and networking opportunities. This center aims to promote the growth of engineering community in Kottagudem and the surrounding areas by providing resources, knowledge exchange, and opportunities for professional development. On behalf of Kottagudem Local Center and my own behalf, I extend my warmest welcome all once again, and I request Professor V. Ramu, Assistant Professor, Triple E Division, Kottagudem University College of Engineering, Kakatiya University, Kottagudem, to introduce the panelists. Thank you. Ramu Garu.
Thank you, sir.
Okay.
First of all, respected Ram Mohan Sir Garu, Chairman, IEI Kottagudem Local Center, and Honorary Secretary Banda Srikanth Garu, Joint Secretary Pranab Kumar Sir, and all other members of IEI Kottagudem Local Chapter, Local Center, and all the panelists as well as the participants. A very good evening to one and all. It's my privilege to introduce Sri Ramesh Jundra Garu, Additional Manager R&D Department, Singarani Corliss Company Limited, Kottagudem. Sri Ramesh Jundra currently working as an additional manager at Research and Development Department of Singarani Corliss Company Limited, Kottagudem, India. He is in charge of Strata Control and Numerical Modeling Cell, Kottagudem region of Singarani Corliss Company Limited. He is pursuing his PhD from IIT Kharagpur. He did his dual degree MTech and BTech in mining engineering from IIT Kharagpur in the year 2011. He received Best Officer of R&D Department from Director P&P for the financial year 2022-23. He conducted 62 number of various scientific studies pertaining to underground mines, 44 numbers, and open cast mines, 18 numbers of SCCL from financial year 2017-18 to financial year 2024-25. Based on which the mine authorities got working permission from DGMS. He received Pratibha Award for Excellence in Intermediate Public Examination held in 2005, awarded by the Government of Andhra Pradesh. He received Pratibha Award for Excellence in Secondary School Education Examination held in 2003, awarded by Government of Andhra Pradesh. He received Pratibha Award for Excellence in 7th Standard Examination held in 2000, awarded by the Government of Andhra Pradesh. He has been working on FLAG 2D and 3D and Galena software for support design in underground workings, pillar stability analysis, slope stability analysis of high walls and overburden dumps in open cast mines, etc. His areas of interest are rock mechanics, numerical modeling, design of underground workings, slope stability analysis in open cast mines, etc. So with this small introduction, I would like to uh, I heartily welcome Sri Ramesh Dundra Garu into this session in the technical webinar. So I request Sri Ramesh Dundra Garu to continue his session in this technical webinar. Thank you, sir. Thank you for giving this opportunity to introduce Sri Ramesh Dundra Garu. So I request Ramesh Dundra Garu to continue his session.
So, thank you, Ramagaru. Ramesh Garu, please start your presentation.
Yeah. Thank you, sir, Mr. Ramagar, Assistant Professor, and good evening to Sri Ramon Garu, Chairman, IEI, Kottagudem Local Chapter, and Honorary Secretary, then Joint Secretary, and other members of IEI members, then participants, everyone, all of you, good evening. In this, I firstly thank you, IEI, Kottagudem Local Chapter, for giving me this opportunity to share my knowledge on numerical modeling, application of numerical modeling in our mining activities. So I thank you once again for giving me this opportunity. With this, I will start my presentation. In this presentation or in this webinar, I am going to briefly talk about the various different types of familiar numerical modeling methods available, and also its application in mining industry, particularly in mining industry where we do really require the application of numerical modeling. Okay. So actually, what is in a brief, what is exactly the numerical modeling? Numerical modeling is a simulation technique that uses mathematical models to replicate the physical processes. Like mining is such a activity, we have to deal with the naturally formed earth. Like we say in technically, we call it as rock mass. So which includes material plus various geological features like joints, discontinuities like that. So we do not have any control or any possibilities to control or to manipulate the formation of the rock mass. So in that case, what we need to do is we cannot do several experiments, and simply, as most of you might be from mining background, for a single instance, I can say, if you want to design a pillar or a gallery at about 100 meters of depth, as well as at about 500 meters depth, both may not be the same. So, but in from practical point of view, you cannot go at 500 meters depth and excavate and test it. So that is very difficult, and it's not possible also. So in that cases, this simulation is a best or better or best tool to at least to get some idea. Numerical modeling may not be 100% accurate. It mainly depends on how correct data or how uh, data you are giving is also matters. So in that case, so it is a best option to simulate that conditions and simplify it our conditions. Then we simulate the conditions, then we will see how much stress is coming, how the sides are behaving, how the roof is going to stand. So like that we can go on add, okay, using this numerical modeling. So it uses numerical methods like finite element method, finite difference method, FEM you call, FDM method, then also boundary element method. These are most popular numerical techniques available. And based on these numerical methods, various softwares are available all over the world. So, okay. As I said, mining, why it's important to have or apply numerical modeling in mining. Mining involves complex rock mechanics and structural behavior. As I said, it is very difficult to do practical like testing like that. So, and behavior of rock is very, very complex. So in order to improve our safety and enhance the production, so our final motto of the mining is to get the productivity with safety. Okay, these are some of the numerical methods and softwares related to those particular numerical methods. Finite element method. In this one, broadly, if we say it divides if you are given a geometry, it divides that geometry into, like, if you say this is my interest, area of interest or my domain of analysis, so it divides this into simpler parts like this. It may be quadrilateral or triangular. It can be any shape. It can be triangular with three corners, or with 6 corners like this in the middle of the sides also. So it divides the domain into elements. We call these small portions as elements. Okay, so like that. Abacus, Phase 2, ANSYS, these are some of the softwares developed based on the finite element method. Then coming to finite difference method, it see, as most of us, many of us know that rock mechanics mainly, like if you can see your basic rock mechanics background, so most of us used to solve the partial differential equations, or even some cases for conversion of stresses to strain, strain to stress. Then we need to multiply with very higher dimensions of matrices. So, so mainly rock mechanics involves a lot of, many equilibrium equations are partial differential equations only. So those our main aim is to solve those partial equations. But it is very manually, it is very difficult to directly solve those equations. So in order to solve those equations, in majority of the cases in FEM, they solve at each node. So it will estimate the displacement at this point, then at this point, then like this. So it will calculate all the required variables like displacements, velocities, or forces at this point. So like that, then after calculating at each node, okay, if you divide a part like this, so after calculating at each node, it will combinedly, it will give the result. Then it will assemble all these node variables, and it will give us our final results. So we call it as a discretization. In FDM, it will what it does is it whatever partial equations are there, partial differential equations are there, it will solve. Later also I will briefly explain about it. It will solve those by approximation, then they will give the results. Our main aim is to solve and to find out the variables like displacement, velocity at a given point or within the zone, our area of interest. Okay, if you know the displacement, or from that you can calculate the strain, displacement to strain, you can calculate. From strain to stress, you can also get that. Stress to force again, or you can also force, also you can directly calculate it. So all are interlinked. So our main aim is to estimate the field variable within our area of interest. Then coming to boundary element method, it is the simplest one. It what does it do is it estimates the value equations or values at the boundary of a instead of discretizing it the whole domain, it do only, it will discretize the, like, discretization means dividing into small elements or parts. So boundary, it will discretize the boundary, then it will solve those equations, uh, solve those equations at this boundary. Then using that, it will get some equation. Using that equation, we will also estimate the given our area, our interested variables within the domain. Okay, so that is a boundary condition. Examine 2D. It is very useful for a simple geometry domains. For complex, it may not be much advisable. Boundary element method. Then discretized element method, or discrete element method, or distinct element method, both are same. In the first three are, we call them as a continuum models, continuum methods, where there will not be any separation between these elements, and the nodes of adjacent elements will be always joined together. There might be a movement may be there, but they will not separate. So but practically it may not be the case. When we see in mining, we have seen, you may have seen roof falls, side falls, and roof collapse in the Gulf means already excavated area. So that means that material is falling without any contact to the its parental rock. So these first three may not be completely 100% representing our uh, field conditions, but however they will give some idea for us how it behaves. But in order to simulate our practical and exactly the field conditions, and now very recently, this method is came into limelight. So it mainly models the interaction between the particles. So it may be a particle, or it may be some block, so how they behave like this. So we call it as a discrete element method. Okay, so UDEC, universal distinct element code, or PFC, particle flow code, these are some of the softwares which are developed based on DEM. It is most suitable for analysis of stability of orbit dump. As we know, orbit dump is a loose material, broken material dumped at one place. So their interaction with particles or boulders or blocks is very high there as compared to the underground or high wall benches. Okay. So finite element method, it is the most well-known and powerful numerical tool to study, predict, and model the behavior of the material. In our case, mining material structures and fluid events, like even not only numerical models are also applicable to mechanical as well as fluid, like fluid mechanics also. Material structures means, in our case in mining industry, as we are working in coal mining particularly, so underground excavations or underground pillars, galleries, or even if you go to, if you consider metal mines, we may say room and pillar. In that case, stove design also can be done. Then in coming to open cast mine, high wall benches, and also overburden dumps. So these are the structures, so that can be studied, their stability, or how much stress is coming onto the foundation or material, whether it will be stable or not. We can find out many things from using this finite element method. So the primary steps in finite element methods are domain discretization. As I said in the previous slide, we'll discretize our domain of interest into small parts, which we call them as elements, which are connected by the nodes. Okay, that shape may be triangular shape or quadrilateral shape, two-dimensional. Okay. Then a local approximation of field variables. This one also I have mentioned in the previous slides. So we will estimate the field variables like displacement, forces, like that. Then assemble of elemental matrices, from that elemental matrices to a global matrix and its solution. We'll assemble them, then we'll find out the solution. But this can be done with aid of computer. Highly advanced computers are available nowadays. So with this technique, manually it may not be so easy. Can be done, but for a very small, like a analysis of a hanging rod or a beam or like that. But if you go for 3-4 no elements, uh, uh, a body consisting of a like 3-4 elements, uh, this may be manually calculation of estimation of failure at these locations will be very difficult. So because of the reason, we need this numerical modeling techniques. Finite difference method, it is the oldest one to solve the partial differential equations of engineering problems. As I mentioned, our rock mechanics also involves a lot of partial differential equations to estimate the variables at our required positions or required areas. So in this method, uh, the main principle in this finite difference method is the partial differential equations are approximated into a system of algebraic equations. So of field variables like displacement at grids of nodes by using difference methods over a certain spatial intervals delta x, delta y. So in this case, what we do is, if you see, for example, if you consider a graph like this, so this is x and this is y. So if you want to estimate the if its equation is dou x by dou y, okay, okay. So this is the range. Okay, this is x1, x2. This is x1, y1. This is x2, y2. So if you really want to solve it, we have to integrate. Okay, with respect to x, if you want to solve it, x1, x2, or y1, y, like that. If you want to solve it, this is the integration we need to do. Okay, then it becomes. But in finite difference method, what it will do is it approximates it like this: delta x by delta y. So we can write directly x2 minus x1 by y2 minus y1. So it represents, instead of this curvy nature, we approximate it as straight line. This is nothing but the slope of this, inverse of slope of this one. Okay. So this is what in FDM we do. Okay. So these approximation, we will approximate the partial differential equations to algebraic equations. Then based on the system of algebraic equations, then the system of algebraic equations are solved by incorporating the boundary conditions. Okay. So I hope majority of, if you are a mining engineer, you might have know it. So if you make any excavation, like if you are driven a shaft or tunnel, we learned in many, in rock mechanics they might have told that when, if it is radius is a, okay, after at about a distance of 5 times of that radius, okay, we learned that using Kurt's equations, after 5 times of this radius of tunnel or shaft, it's this shaft influence will be nullified after 5 times of the distance. So if you go from here, center of this shaft or tunnel to this point, this location, at this location, influence of this excavation is almost zero. So then what we do is, if you want to analyze a tunnel, two-dimensional, we select the boundary in such a way that in our model, see, our earth is a continuous, it's a round and it is continuous. We cannot model, or we cannot analyze the complete that earth, right? So we need to, in order to, for efficient and fast analysis of numerical modeling, we need to simplify our model in such a way that results should not be compromised. At the same time, it is solved very fastly. So that should be kept in mind. So for that reason, as I said, based on this, at least if it is radius is 5, example, see, if it is radius is 4, okay, so at least 20 meters should be extended up to this, so that we can also we will get the actual behavior or actual influence of this tunnel or excavation on the surrounding rock. So then what we do is we apply here displacement is, after this the deformation is 0, as we already know that after around 5 times of that radius, it is 0, its influence is 0. So then we can cut it, we can model up to this one, we can consider up to this one. So here we apply velocity or displacement is 0. So here displacement is 0. So the, so also with our experience and all from the available literature and all, so we applied displacement as 0 at this location. So this we call it as a boundary condition. So similar way, in similar way, if you go downward also, upward also, so we can consider up to 5 times. So minimum it should length should be 5 times. So after that, its influence is 0. So deformation of the rock is 0. So here, so the deformation 0 means strain is 0. So indirectly stress, induced stress, not as we know, there are many stresses are there, like horizontal stress, in situ stresses, then induced stresses. So means stresses due to any excavation. The stresses induced due to any excavation are called induced stresses. So after certain distance, its deformation is 0. That implies that stress is also 0. So we call this displacement 0 at certain distance, stress is 0 at certain distances. We consider them as boundary conditions. Okay. So boundary conditions plays a vital role in solving the any our rock mechanics problem or analysis of any structure or domain. So coming to boundary element method, The basic principle is to fit the boundary values into the integral equation using the given boundary conditions. So, as I mentioned, we can also see, you can also consider up to displacement zero boundary, or we can also consider up to here, and you can also roughly estimate the displacement that may be possible here and give it as a boundary condition. So, see, in numerical modeling, the main thing to keep in mind is one of the main important points to keep in mind is uh, larger the size, larger the size of the model, then number of elements will be higher. So computational time will also be higher. So all are directly proportional. So in order to keep it very simple and to compute it fastly, you can also optimize your model so that it can compute it very fastly. So for that reason, you may also consider up to here only, but your boundary condition may not be as it is here. So here we need to give some displacement 5 centimeter or 2 centimeter like that. Okay, so in that way, we will at a boundary, we will using boundary conditions, we will solve those integral equations. So for that solving, discretization is needed at the boundary only. Okay, so no need of any discretization within the domain, as I mentioned earlier. So after finding the solution on a boundary, so after substituting our boundary values in the equations, we will get some equation pertaining to that special domain, that particular domain. Then using that equation, we can also directly find out our field variable inside the domain. So first, initially we will estimate the equation pertaining to this boundary using boundary conditions. After that, we will get a simplified equation. Using that equation, we will find out our field variables within the domain. So the main advantage of this boundary element is reduction of model dimension by 1. It is a 2 dimension. Okay. So, but here we are discretizing only the boundary. So nothing but it is almost 1 dimensional it becomes 1 dimensional only. So if you take a 3 dimensional, okay, so volume. So if it is a 3 dimensional, then we will discretize the only this boundary. So in 3 dimensional, we will discretize the area. So this becomes the boundary. So we will discretize it. Okay, like this. So on all 6 sides, we will discretize it. So it is becoming 2 dimensional. So 3 dimensional problems are converted to 2 dimensional, and 2 dimensional converted to 1 dimension. Okay, that is the advantage of this. But the main drawback of this boundary element is it is not applicable for a complex geometry. If you want to analyze a simple geometry, then is okay. But if you want to model any like a D-pillaring operation like that, so it is very difficult because D-pillar operation may not be represented by may not be solved by this, because the debugging involves a lot of activities. So in that case, it may not be much applicable for that. Okay, next, discrete element method, as I mentioned earlier, it was developed to model the discontinuous behavior of rock mass. Okay, so including as it simulate finite displacements and rotations of discrete bodies, including their detachment. As I said, these after discretization, these elements may get detached also. So in order to analyze this type of behavior, the discrete element method is came into picture. The main concept is to treat the domain of interest as an assembly of particles or blocks which are continuously interacting between each other. So they interact with each other sometimes maybe be attached to these nodes are attached to each other. Otherwise, they may be discretized. They may be separated. Okay. So these are major. There are many other like hybrid numerical hybrid methods are also there. So finite element plus a discontinuum, DEM like that. But these are some of the methods. So application coming to mining engineering, where do we normally apply in a broader sense? So slope stability we do, stability of the open pit high walls and OB dumps, then predict the potential failure zones under different stress and pore water pressure conditions. So underground excavation design, we do short pillars, short shaft design, tunnels design. In metal mines, we will also design stopes. Then also we can also optimize the support design. See, to prevent side fall and roof falls in underground excavations. Okay, so if see, we do mining for financial benefit only. At the end, we need to look at the financial benefit of mining. Okay, so for that reason, optimum support design should be done. Like instead of you cannot put every one bolt for every 0.5 meters and we say it as a stable, like safe. So, but it also involves a lot of revenue, money. So for that reason, we need to optimize our support design. So we should get the production at the as well as we should ensure the safety. For that reason, optimum design of support is very important. Okay, then we can also substance prediction. Nowadays, we are doing mining beneath many structures like roads, houses, private houses like that. So in that cases, how our excavation will affect the surface is also very important. So those surface structures should not be affected by our mining activity. So in order to that, how we can simulate different permutations and combinations so that we can come to some conclusion and we can adopt the best suitable method of extraction. Okay. So we can also rock mass behavior and design. We can also do that one. Okay. Then coming to case study one, this is I mentioned it as a case study, but as you all know, particularly mining engineers, mining students or mining engineers, we do estimate vertical stress by tributary area method. We know many people. In this case, we assume that if it is a coal pillar, okay, sorry, it is a coal seam. So stress normally, vertical stress are normally it flow like this. So it passes like this. So, but if you make any excavation like this here, okay, so this stress, it need stress for transfer of stress, it requires medium continuity in the medium. So once you make any excavation in here, the stress will bypass like this. So like this. Okay. So normally we assume that it will redistribute it. Then normally if stress before excavation, if it is 2.5 MPa, after making opening here, it may go up to 2.7 or 2.9 like that. So roughly for example, I'm saying, so the difference, whatever may be there. So because of this one, the stress is increasing, which needs to be smaller than this one. So we call this as a redistribution of stress, induced stress, as I mentioned earlier. So we actually redistribution of stresses due to excavation are called redistribution of stresses is called induced stresses. So we assume that the stresses, if 2 megapascal are coming down like this, we assume that 1 megapascal goes this way and then 1 megapascal goes this way. Whatever may be the stress which has to be redistributed, it will be shared equally by this side, and this side. Okay, so that's why here. Okay, so this is tributary area concept. Let us consider a pillar of 50 by 50 meter size, center to center, situated at 300 meters depth. Okay, gallery size is 5 meters and 5 meters width and 3 meters height. Okay, normally by tributary area concept, the stress is given by this formula, estimated by this formula. H is the depth. You can also, gamma is the unit rock pressure, 0.025 MPa per meter. Generally, we consider for coal mines. Okay. WO is the width of the gallery, width of the opening or gallery, 5 meters. WP is the width of the solid pillar. So 50 minus 5, 45 meters it becomes. Now the vertical stress on the pillar is around 9.26 MPa. So for this one, for estimation of a pillar at a given depth is very simple using this tributary area concept, for which we do not require any numerical modeling. Okay, but I will show next case study. In this case study, we come to know the exactly why you require numerical modeling. Okay, so my even in this webinar, I want to make you understand that the importance of why you need a numerical modeling for mining also, because all mining conditions are not same. Okay, so in order to ensure safety and also to get the productivity, we must before going mining, we must evaluate our conditions. Okay, so this is a CM continuous miner panel 12A in King Sim of VK7 incline. Presently the mine is closed. Okay, fortunately I got the opportunity to study this panel and give support design manner of extraction during COVID period. So I am going to present this one. So here CMP12A, it has two sub panels. CMP12A1, we can say, I think it is very small. CMP12A2, okay, these two are sub panels under CMP12A. So in this one, it has 9 pillars. It has almost 14 pillars. Okay, so they adopted diagonal line of extraction. First they extract this one, then 2, 3, 4, 5, 6, 7, 8, 9. Similar way, 1 first pillar they will extract this one, then 2, 3, 4. So diagonal line of extraction they do. Okay, lastly this one. Okay, so they adopted diagonal line of extraction. Same here also. So here, what happening is, these are normal details of those two sub panels. They are around 290 meters depth from surface. Okay, so number of pillars in panel 12A1 is 9, and is in 12A2 14 pillars are there. Here what happened is, actually before going to that one, I want to give a small brief about extraction of coal by continuous miner at VK7 incline. Initially they introduced VK7 continuous miner in King Sim. So initially in first 4 panels they adopted non-caving yield pillar technique. As you know, yield pillar means designing pillars of coal to intentionally fail in a controlled manner. We want to fail that, you want that pillar to fail, but in a controlled manner, so that by that time before before failing of its failure, we want to extract at that location and come out. So in that way we will design the pillars. Some pillars we will left to failure. But what happened is, after extraction of 3 panels successfully, in the 4th panel, So almost out of 20 pillars, they could extract only 11 pillars, and they had to close that panel without extracting the remaining 9 pillars due to strata control issues. So in that one, they adopted a straight line of extraction. So as I mentioned here, diagonal, say they adopted straight line of extraction like this. Okay. Okay. So that later what they did, they changed the yield pillar, non-caving yield pillar method to the caving method. But with a straight line of extraction only, they successfully extracted 7 panels. Later in, so the next panel, 8th panel with the caving, they could only, one pillar they could extract out of 9 pillars. Later they had to close that panel due to severe what do you say, strata control issues. You can imagine, out of 9 pillars they could only extract 1 pillar, and remaining all they had to close that panel due to strata control issues. That strata control issues arise due to presence of long wall gouge and barriers in the top seam, which is lying above the king seam. So if you say this is the king seam, okay, so top seam is there. They may also call it as queen seam. So in this top seam, there are long wall gouges and barriers. So what they observed is when long wall panel is, if it is a long wall panel already extracted, and these are the barriers. Okay, so if it is a king seam, so this is gallery. Okay, this is a pillar, and this is a gallery. This is the pillar. Okay, this is gallery, and this is pillar. What happened? They found that when long wall in king seam, if the partition is around 40 to 50 meters only, less than 50 meters. Okay, less than 50 meters. Okay, so from panel to panel it may vary from 30 to 40, 40 to 45. In this panel it is around 43 meters only, so less than. So when the partition is less than 50 meters between two seams, and the overlying seam contains any D-pillared panels, caved gouges, or even stored gouges also, then the stresses, there will be a stress over extra stress on the pillars falling beneath the barrier of the top seam, top workings. See, as I mentioned in earlier tributary area concept, see, stresses used to come like this before mining, but when you excavated this one, these stresses need to redistribute like this. Okay, okay, like this. So here it has a continuity in the medium, so it directly comes down like this. Okay, so because of this thing, so normally what should, if it is a virgin, this stress should come like this, then it should go like this. But what happened is here, because of this redistribution above this one, additional load is coming onto this pillar. So the pillars which are falling beneath the barriers of the top seam, overlying seam, are highly stressed than the when the top seam, this overlying seam is virgin. Okay, I will show you. You will clearly understand in next slides. So coming to pillars falling beneath the gouge of top seam or overlying seam. So here no stress is coming through this gouge. Yeah, it will already, pressure arch theory. So your gouge will form like this. So stresses will go like this. So here there no stresses are coming from the top. So the only load coming on to this pillar beneath the gouge is the overlying burden, whatever maybe is there, it is there. So if you are at 290 meters or 500 meters, the weight that is the load that is coming onto the pillars falling beneath the gouge is only the partition weight. Okay, here also same. This pillar is heavily loaded due to redistribution of the stresses on the because of GOF in the top seam. So in this case, you can see in panel CMP12A1, one conventional LHD depillared. This is a GOF. This black, you can see this black portion, you can see. This is a gored out panel, caved out. Actually, it is caved panel. Okay, LHD panel. Here, this is the long wall GOF. This is a barrier. So here, the CMP12A2, it is adjacent to, it is falling on the barriers, and the pillars are adjacent to the barrier of the long wall in top seam. Okay, so for this analysis, see, I did for this analysis, I did numerical modeling for 2 cases separately. So here you need to understand another one more important thing is, when we are going to, firstly we'll excavate this panel, then we will go to this one. When we complete excavation of this panel and go to this panel, this part also becomes GOF. So while modeling CMP12A2, we must also consider this as a GOF. So GOF adjacent to this CMP12A1. Okay, these are the 3D grids showing CMP12A1, 12A2. Okay, okay. So as I said, this is the adjacent GOF, and this is the top GOF, which I said T12 panel in top seam. The partition between top seam and the king seam is around 43 meters in this case. So coming to CMP12A2, as I said, part of the GOF is coming onto the barrier pillars here. Okay, this is one pillar I had GOF of panel number 12, conventional panel, LHD panel. Then GOF of CMP12A1, as I mentioned, after completion of this panel, we will go extraction of this panel. But by the time this becomes GOF, so in order to evaluate the actual condition, field condition, I consider it as GOF for the analysis of the CMP12A2 panel. Okay, so this is the stress. So vertical stress on pillars of the subpanel CMP. This is the 9 pillars are inside the panel. So vertical stress. So this stress is when the top seam, as I mentioned, when the top seam virgin, you can see the stress is very, in each pillar is very symmetric. So if you graph it, it is almost symmetrical in 2 directions. Okay, so symmetry, and the stress ranges from orange like 7.5 to even green almost to 9.5, 10. You may say 10. At corners, it may go up to 12 also. Okay, this is okay. Don't confuse about this minus symbol. In most of the softwares, minus symbol indicates compression, plus means tension. Okay, so here the stress is around 7.5 to 9.5 MPa. Okay, but when the top seam is virgin, this is the condition. But when the top seam is excavated or goved out, caved, this is the black outline. You can see this is the outline of that panel which I showed here. This is that panel. So when the top seam is there, you can see clearly here. This is the goved out. So these pillars are which are falling beneath the GOF are de-stressed. You can see here red color minus 6 MPa to very 10, not even 10, 9, 10. If you take average, it will be very not that much high. Okay, this one also. Okay, see here the adjacent. So if it is gored out, then this becomes barrier of the top seam, right? So these are little stressed than the virgin seam condition. So you can see here 9, 8 to almost 12, 13, even it went up to 13. So the pillars which are falling beneath the barrier of the top seam are highly stressed, and which are falling beneath the gulf of top seam are de-stressed. Means stress has reduced than the actual when the top seam is virgin case. Okay, so similarly, this is the vertical stress on the pillars of 2A2. Here the uh, that de-stress may not be there because no caved gulf is exactly present over the vertically above this panel, but the long wall face line has come up to here and stopped here. So due to that, these barrier pillars and this and one gulf, adjacent gulf would be there after extraction of the CMP2A1. Because of this reason, these pillars are little stressed. Highly stressed than the virgin condition. So this is virgin condition. This is with GOVs in the top seam and adjacent panels. Okay, so it figures may not be that much clearly. From table you can see. So this table represents the seam dual A1 9 pillars. So when the top seam and without any adjacent workings, top seam is virgin. Okay, the stress are around 9.1 or 9.8, 9.05 like this. Okay, so stress is like this. But with the overlying and adjacent workings, stress is not uniform in all over all the pillars. You can see a maximum of 10.5 reduction in the pillar number 3, which is falling. So you can see this is 1, 2, 3. So this is the 3, pillar number 3. So this is highly de-stressful. Then pillar number, this is 1, 2, 3, 4, 5, 6 also. So then again 2. Right. So then 2, 4, 5 should also get some increase in the, yeah, you can see 4. Okay, so like that here also 2 also there is a increase in the stress 7, then 4 also increase, maximum is 9.3 increase in the stress. So this indicates that when the top seam is virgin, the stress is very the uniform stress is present over all the pillars, almost similarly same value. So if it has some caved out panels, then the stress on the pillars varies depending on their position, whether they are falling beneath the bearer of that top seam panel or gulf. So you can see wherever the gulf is there, beneath the gulf are there, their slight reduction. This one, 3 pillars, and remaining they are falling beneath the barrier, so they are experiencing higher stress. So when if the top seam is virgin, then they should have only 9.08 MPa. But due to that presence of barrier of caved out panel in the top seam, it has increased to 9.53. Okay. In similar way, there is a maximum of 5.2% increase in the stress on pillar 1. Okay. So this way, see, this way these numerical modeling is very useful. Okay, so my clarification, my simplification is that here you can also, these are we can say empirical method or like tributary area method, we can estimate, but in this case we do not have any option to incorporate the presence of the top seam overlying workings condition. So do you have any option to here? We do not have any representation of that particular condition. So it may be helpful for simpler and simpler condition, ideal condition, you can say, without any adjacent workings and top workings. You can use it very straight away. You can use it. Okay, but if you have any special conditions like this, okay, so these tributary area method or empirical methods are not suitable, not applicable. Okay, so as I mentioned in earlier, when the eighth panel with caving was extracting, while extracting the eighth panel with caving and straight line of extraction, they faced a lot of problems due to this reason. So after that, they analyzed, SIMFER, Central Institute of Mining and Fuel Research. They analyzed the uh, impact of that top sim goes and barriers. Then they understood that it is overloading. Some pillars are overloading and some pillars are underloading due to the presence of GOF and barriers in the top sim. So after that, they advised to go with the diagonal line of extraction. So in diagonal line of extraction, that hanging GOF will be supported by the solid pillars. So that is the advantage of diagonal line. But movement or rate of extraction may be little slower than the straight line of extraction. Okay, that is operational difficulty will be there. But safety wise, they advise to go for diagonal line of extraction. So this is the main real application in the field of mining. Okay, application of numerical modelings in the field of mining. So this is a practical case which we dealt in VK7, one of our coal mines in Kottagudem area of Singareni. Okay, so the numerical modeling methods are not only applicable to rock mechanics, but they are also applicable to mine ventilation and fluid flow to design the as per regulation 153 of CMR 2017, at least 6 meters per minute per cubic meter of air, 6 cubic meter of air per minute per person, or 2.5 cubic meter of air per ton per minute should be available. So in order to comply that one, we need to design ventilation also so for that one also, like VentSim software is there. We can simulate the ventilation circuit in the mine, and then we can design optimum ventilation to comply the standards, CMR standards. Okay, so then blasting and fragmentation analysis can also be done to prevent mainly to improve the fragmentation and productivity, and also to prevent or control the effect of ground vibrations on the surrounding structures which are not belonging to owner, like mining, you can say Singareni in our case. So because nowadays most of the open cast mines are operating very near to surface structures or roads or private houses. So there we should take care of uh, restricting our ground vibrations, so that that in that case we need to do optimum blast design. For that one also, you can use blasting this numerical modeling techniques. Seismic risk assessment, it can also be done. Then hydrogeological modeling, how water flows and how much pumping arrangements are required, they can also be done. Okay. Then so those are applications in mining. So benefits of numerical modeling, as we are discussing from the beginning, design accuracy improvement, trial and error in the field, which we cannot do in mining particularly. See, in other cases, in case of a mechanical engineer, if you want to design a structure, you can manufacture a definite composition material or rods like that, and you can test it in the lab. If it is not sufficient, you can change it. But in our case, mining, we do not have that option. Even civil also, composition, concrete grades are there, M20, M50, like that. They can directly they can achieve that strength. But mining, we do not have any control on the strength. So if a solid pillar is there, it will have some strength. But if it has any false joints like this, its strength reduces drastically. In this case, we cannot do much. We do not have much operation. So keeping in view of these discontinuities, we should plan accordingly. So numerical modeling enhances the safety of workers and infrastructure. Cost optimization, predictive models, like as I said earlier, support design, optimum support design, and optimum gallery size, like that. Okay. So, but it is more advantageous, but it has some limitations, challenges, and limitations. Requires accurate input data. So, uh, so we call it as GIGO, like garbage in, garbage out. So if you give very accurate data, your results will be near to accurate. Okay, if you give false data, wrong data, then your uh, results are also false or wrong, incorrect. Okay, so whatever you give, that will be reflected in your results. So, so before going for any numerical modeling analysis, we should keep your data to the maximum possible accuracy. Okay. Computationally intensive for large models. So as I mentioned in CMP 1, so it's a very large model. So it required very computational capacity. Like, it takes a lot of time. So it requires high computer, what we say, computer capacity, like RAM and all. Configuration is very high. We need for solving large models. Configuration of the computer is also very, very important. May not capture all geological complexities. So in this case, we cannot model all the faults, joints, small joints are there. We may not capture all those geological complexities. Then interpretation of results requires expertise. So as I said, if you model something, if you give some properties, and if you run the model, it will give you some results. But we should have some expertise to see whether that results are correct or not. Okay, that is also right. So first and last points are very related to each other. Okay. So we can conclude that numerical modeling is an essential tool in modern mining, as Sri Ramohan sir rightly said in the introduction part, that it is a modern mining. In modern mining, it is a essential tool. It improves decision making, safety, and sustainability. As computing power increases, its role will become even more critical. Requires good data, skilled interpretation, and suitable tools. Okay. With this, thank you. I hope that people got some insight into the numerical modeling.
Okay, thank you, Mr. Ramesh Garu. After completion of second presentation, question and answer session will be there.
Okay.
You can exit from your presentation. Now, just for the participants' knowledge sake, I'm telling in the panelist is same. Actually, in fact, the Singareni Colliery mines was invented by Dr. William King, geologist. On his name, all the main seams in Singareni Collieries are called as King seam, and next the Kerr seam will be called as Queen seam. Actually, our Singareni Collieries, the Singareni Collieries complete breed started in 1889. The core was invented by Dr. William King around 1880. Just for information, I'm telling. Now I'm requesting Sheikh Hafizuddin, Senior Electrical Engineer, SS Limited, bottling unit of Coca-Cola industry, to introduce the next panelist, Sri C.H. Ravikiran. Thank you, Ramesh Garu, once again. Now I'm requesting Sri Sheikh Hafizuddin to introduce the panelist, Sri C.H. Ravikiran. Hafizuddin Garu.
Yes, good evening, sir. Good evening to everyone. Sir, am I audible to you, sir?
Okay, your voice is okay. Please continue.
Sir, good evening to every delegate. And in today's webinar, it is my privilege to introduce the CH Ravi Kiran Garu. He is currently working as a lecturer in the Department of Mining Engineering. He is coordinating the class of BTech Mining and is pursuing his PhD now. And he did his BTech in the Department of Mining Engineering from the University College of Engineering, Kottagudem. And he is well versed from the he is well versed in the AutoCAD, ANSYS, Galena, Phase 2, and RSLIDE2, Blastware, Flag 3D, Flag 2D, Slope, Surpac, Minex, Abacus, and QGIS, Flaxis, WIPFrag. And his areas of interest are mine planning, surveying, remote sensing, GIS and drilling, blasting, rock mechanics, and numeric modeling, slope, stability, safety management system, and environmental management system. He published various journals and conferences. With this brief introduction, I cordially invite to CH Ravikiran Garu to start his presentation.
Thank you, sir. And thank you, Raman Garu, Srikant sir, Karnakumar sir. Sir, am I audible, sir?
You are audible. Okay.
Okay, thank you. In the before presentation, as our senior Sri Dunda Ramesh Garu told, he gave a brief introduction about different applications of numerical modeling. In this particular thing, I will limit my presentation with reference to the subsidence prediction. Basically, my presentation for today is application of numerical modeling with reference to subsidence prediction. Basically, numerical modeling is nothing but it is a combination of different types of equations to get a solution. These will be made in the simple mathematical equations, and we will get a final solution. That is nothing but numerical modeling. Why the importance of numerical modeling is important in mining means there will be n number of probabilities. In mining also, we will take these different types of probabilities and we will employ different sequences, and we will apply these permutation combinations and to get a proper result. It may give it will give us a proper justification, or it will give a proper path to do a proper mining activity. So now numerical modeling as of day is gaining its significance in mining. These are the different applications of numerical modeling. Though there are many, these are some of the applications of numerical modeling that are strata control, ground design, slope stability analysis, mining sequences, subsidence prediction, risk management, longwall top coaling mechanism, and groundwater dewatering simulations, and mine environment predictions. These are some of the major applications with related to our numerical modeling in mining. As I told earlier, my scope for this presentation will be with reference to subsidence. As we all know, subsidence is nothing but it is a phenomenon in which the Earth gradually sinks because of the different types of man and natural activities. The phenomenon of this particular feature of tending the surface to dipping is considered to be our subsidence. There are basically natural and man-made activities of subsidence. Natural activities are basically earthquakes, tectonic and crust activities. Man-made activities are mining, groundwater extraction, or removal of any soluble materials, or like oil or natural gas. These will come under man-made activities. This is rough representation of a subsidence phenomenon. This first column will give you the initial phase of this particular surface. The second column will give you the process of extraction of different types of, like natural gas, mining activity, or dissolution of limestone with reference to the groundwater, or any groundwater traveling, or groundwater seepage or permeability of this particular groundwater. This particular thing may happen. After this particular phenomenon, the third slide, the third column will give you a rough sequence of the surface damage that is happened with reference to these different conditions. Basically, in this particular phenomenon, there are different types of substance phenomenon, but I will in substance also I will limit myself with the mining induced substance. Mining induced substance is nothing but the uh, this particular the picture will give you a rough sequence of mining activity. Bottom here, the material is extracted because of this extraction of this particular material. The material which is on the surface may tend to move downwards, thereby causing the material to have thereby causing the surface to tend downwards. This creating a downward displacement. Okay, there may be multiple factors that are involving. There are multiple causes with reference to the substance. These are some of the factors that are influencing substance that are effective seam thickness. Means if the seam thickness is 1 meter, or if the seam thickness is 2 meters, if the seam thickness is 3 meters, depending upon the seam thickness or depending upon the method which we are which we are working, the substance may be in some cases it may be a bit low. In some cases it may be high, as well as multi seams. Multi seams means if there are 3 or 4 seams, means if you are having first seam, next an introverted, next another seam. If you are extracting the first seam and or okay, these red lines, let us assume these two red lines are any seams, working seams. This bottom is the introverted seam. Means from this particular surface, we will come into this, come here, this come to bottom to work this particular seam. After working out, we can go for this seam. Means if our sequence is from top to bottom or bottom to top, depending upon this particular sequencing also, the tendency of this particular substance may change. Also with reference to the seam depth, if the depth of the working is at a limited depth of 200 meters or 300 meters, in some mines, as of now, we're working at a depth of nearly 400 to 500 meters. The tendency of this particular the substance is maybe changing with reference to the depth also, as well as dip of the seams. Means if let us assume this particular surface, uh, if the seam is horizontally, it can be considered as flat seam, or if it is a bit declined, or if it is a bit inclined, it can be termed as flatter, moderately inclined, or steeply inclined. With reference to this particular phenomenon, the magnitude of substance may change, or the effect of the substance will change. Okay, these are some of the major things. Among these things, the important one of the important is time lapse. Means with reference to the time also, the substance will have a drastic effect.
Ravikant garu, we are not getting your voice.
Sir, sir, am I audible now, sir? Sir, am I audible now, sir?
Yes, yes.
Okay, these are the factors. These are the major factors that sorry. Okay, with reference to these particular, with reference to that particular factors, the surface may tend to have different types of deformations. Among those, there are majorly the surface cracks or fissures, potholes, or rough substance are the major thing. With reference to the cracks are nothing but the surface deformations are the surface cracks that are formed. On the surface are tend to be are called as cracks. Pothole means nothing but the deformation that is localized deformation in a particular place, or the deformation that is happened vertically above the seam or the particular area can be termed as pothole. Nothing but rough substance means localized or more area wise disturbance is considered to be our tough substance. These are the basic components of our substance. Majorly vertical, as I told earlier, the vertical displacement is nothing but the settlement of the surface from surface to means basic surface to ground downwards, and the horizontal displacement is nothing but the lateral displacement of the surface. The derivative of the vertical displacement to the horizontal displacement is tend to be our slope. The horizontal strain is nothing but the change in displacement to the distance between distance between these two tend to be called our horizontal strain. Among these things, we will majorly our major consideration will be with reference to the vertical displacement and horizontal strain. In horizontal strain also, if the strain is as Mr. Ramesh sir told, there may be positive or negative values. In this particular thing also, horizontal strain, it will be some positive derivative and negative derivative. If the value is positive, it will be termed as a tensile strain. If the value is negative, it will be termed as compressive strain. Okay, and with reference to the maximum displacement or maximum value that is occurred in the substance, our substance can be subdivided into three types: critical, subcritical, and supercritical. If the maximum displacement or maximum value can be observed at a single place, it can be termed as a critical. If the maximum value cannot be observed in our scope, it can be termed as subcritical. If the maximum value is observed at multiple points, then it can be termed as supercritical substance. Basically, from from good olden days, there are multiple methods of prediction of substance. There are theoretical method, profile method, influence method, empirical modeling, physical modeling, numerical modeling. In this particular session, we are discussing with reference to our numerical modeling. Basically, in the last presentation, our panelists told there are majorly four types of numerical modeling techniques, but with reference to the numerical simulation techniques, with reference to the substance prediction method, we have with reference to finite element method in Abacus, Plaxis, ANSYS platforms are the different platforms on which we will predict. And majorly there are different types of things, but the easiness or the ease of working in these three particular software is a bit more than comparing other these things. And with reference to the finite difference model, FLAC 3D software platform is a bit easier. And with reference to this discrete element method, UDEC and 3DEC are the major software techniques with which we will assess our substance modeling. And with reference to the boundary element method, BEFE and FROGDO are the two methods with which are two software platforms with which we will assess or predict our substance. Basically, for all these substrate methods, the steps are basically the outward steps are data collection, model, how to draw a model, and what are the surface with reference to the PMP data. We will adjust the material modeling. Our material modeling means nothing but the density, the Young's modulus, the Poisson ratio, the tensile strength, the compressive strength, which we will get from the field data. That nothing but our PMP data or any mine data with reference to these particular thing, that material properties which we are getting, we will insert this into that particular thing. And after that particular thing, we will apply different types of boundary and boundary conditions. With reference to its boundary conditions, after applying boundary conditions, we will apply, means in some cases there might be some geological faults or some types of disturbances. In those types also we have to apply some control equations. These are the things we will apply. After applying these loads and boundary conditions, we will simulate our model. After simulating, we will analyze the result. These are the basic major steps involved in all the type of software prediction techniques I have told earlier. This is a rough sequence of I have taken with reference to ANSYS. This is a rough sequence. In this particular sequence, we are applying the different material properties to our model. And with reference to that particular modeling sequence, we have constructed a basic rough model. After construction of model, in this particular slide, you can see we have applied different types of loads. That is nothing but acceleration due to gravity, displacement, fixed support, or constraining different models. After this particular thing, we will analysis. In this analysis, we can get different types of results with reference to the components, with reference to the horizontal displacement, vertical displacement, or principal stress, maximum principal strain. These are the different maximum principal strain. These are the different, or we can also get the factor of safety with reference to this particular model. Okay, this is a rough representation of the means. This is just a representation. The model may be. This is let us assume this is an x-axis. Let us assume this working is from this particular corner to this particular corner. I can for my practical easiness, I am considering this particular thing as along the length and this particular thing as along the width. Okay, this is the rough equation of predicting my substance value along the length. This is along the width. This is the horizontal displacement with reference to this particular thing. And the second one is the horizontal strain curve, as I told earlier, the positive value and the negative value. Okay, from these values, what I have done is I have made an a prediction value, means linear progression analysis. I have applied a linear progression analysis. I got a rough progressive equation. Okay, these things all gave a rough sequence. How I am doing a modeling of a longwall mine or underground mine, how I am predicting the subsidence. But we have to have some basic things, or we have to every mine or every particular working should have some basic features to do, because if there were no proper rules or regulations, we will not apply properly. So with reference to these particular things, there are some relevant sections and sections with reference to the Mines Act, CMR, and these things. I am going to show a rough representation of with reference to the Mines Act. Section 18, Section 19, Section 22A will roughly give us the acts with reference to the subsidence, and with reference to the new CMR 2017 regulation 123, regulation 124, regulation 126. These three regulations also roughly specify the regulation with reference to CMR. And with reference to our mine concession and development rules of 2017, there are two rules majorly. Rule 23C and Rule 34. These two rules also are giving us a rough representation to analysis or to predict the substance beforehand. And these are some of the legal and environmental things we have to analysis, or we have to take before working of a mine. Basically, for every mine, before getting the mine, we have to procure feasible. We have to get a permit from our Ministry of Environment and Forest and Climate Control. For that, to get that particular thing, we have to apply. We have to assess our environment impact assessment. In this environment impact assessment also, with reference to the Forest Conservation Act, Section 2 of Forest Conservation Act, the subsidence, the minimum strain, or the minimum strain that we are getting from the particular subsidence should be limited to 20 mm per meter. If our strain is exceeding 20 mm per meter, we should if you are working for open cast, you should get total surface rates. Or if you are working in underground mines also, if your strain is about 20 mm per meter, you should get surface rate also if the amount of strain is more than 20 mm per meter. So for this particular analysis, nowadays most of the mines before starting also they are taking with reference to this particular section. Most of the mines they have to compulsorily analysis, or they have to compulsorily predict the subsidence that is generating from with reference to that particular mine. So as per this particular section, numerical 3D numerical prediction method has become compulsory for underground coal mines, underground metal mines, or any underground mines. Okay, with reference to this particular thing, they have given if our maximum tensile range is between 0 to 20 mm per meter, they have given a table. Means if our with reference to this particular thing, with reference to the surface area, or the forest area, or any natural flora and fauna above on our underground mine, they have made us to find the net present value of that particular surface, and with reference to the how many types of plants are there, how many types of animals are there, what are the surface features, all these things we have to calculate, and we have to project a net present value. On this net present value, if with reference to this horizontal with reference to this strain, if the strain is between 0 to 5, we have to to get the forest clearance, we have to pay some amount. If this particular amount is if the particular strain is between 0 to 5 mm, they will deduct only 25% of the amount we have donated, we have kept for this forest clearance. If the strain is between 5 to 10, they will deduct 50% of our 50% of the amount. If the percentage is between 10 to 15 mm per meter, they will deduct nearly 75% of the amount. If, as I told earlier, if the particular strain is above 20 mm per meter, we have to totally forget that particular amount which we have kept for forest clearance. So nowadays, with reference to this particular thing, subsidence prediction became a major thing, and as well as with reference to in some cases, with reference to the old mines, nowadays National Green Tribunal also giving, or it is acting with reference to the environmental issues. We have to control these particular things. You should work like this. They are giving nowadays. Most of the recent updates are also coming, and with reference to these things, even with reference to in 1984 only, with section 4 circular number 4 of 1984 only, we also got a rough representation how to predict subsidence, or what are the basic sequence of operation of means our Directorate General of Mines and Safety have given a rough representation to how to predict the subsidence or how to calculate subsidence in a particular area. So with reference to these particular things, we have to submit, or if there was any major disturbance or major problem with reference to the subsidence phenomenon, we have to regularly monitor, we have to regularly update our subsidence report with reference to the subsidence report with reference to the normal level surveying or GPS surveying. In some cases, now we are in some other countries, they are using drone survey or INSAR technology or lidar technology. With these techniques also, they are predicting satellite, with reference to satellite imagery also, they are predicting the subsidence phenomenon on a subsidence phenomenon occurring over a mine. So these will all give a legal these will all be helpful in working legally and under proper working thing. Okay, basically, though, what I meant to say is with reference to these particular numerical technique also, if we are properly projecting the value, or if you are not properly taking that particular value, the the particular result may tend to move here and there. So these particular things may project the value, but we can it is not
On behalf of Kottagudem Local Center Chairman, I request
Hello.
Sri Karnakumar Garu, Joint
Yes, sir. I'm in line.
to
Hello?
give the remarks on the panels. Delivery.
sir.
Karnakumar, sir.
Well, sir,
Hello.
it is audible.
Hello, Karnakumar, sir.
Yes, it is audible, sir. Please continue.
Right. Behalf of the Kottagudem Local Center, I am very thankful to the two panelists, the excellent presentation given by today. It's a highly informative for the faculty as well as students, those who are researching the field of the particular really appreciate giving a valuable presentation regarding the numerical application in mining, and particularly prediction of the slow failures by monitoring numerical modeling, playing a crucial role in mining by enhancing the outstanding and the management of geological challenges. And he was giving a powerful tool for the how the prediction of the behavior and optimizing and design of the safety in mining, particularly in rock mechanics and underground mines and slope stability, and also the Gulf Dowd area. Particularly the case studies are very excellent by the near Singran called this a model VK7 mine. It Gulf Dowd area, how the stress is analysis. And also you will nicely explained limitation and continuum and discontinuum methods. And special thanks to the again Ramesh sir. He was a comprehensive challenging even the how the utilization of the numerical modeling in the mining field. And also the Kiran sir will giving the particularly in focusing on the substance role and using the ANSYS software, how the substance behavior in the ground is also very nicely explained. Thanks to both of the panelists 1 and 2. I welcome any audience who would like to ask any question. Numerical modeling in the mining application. I welcome anyone, please.
So there is already one question in question answer. You can read that question and the panelist can reply. Go to the question and answer. The audience can only type the if they have any questions. Okay, you can type any questions in the question and answer section, which will be taken by the moderator.
I think nobody is not given any chart, sir. Dr. Srikant, sir. Dr.
Okay,
Srikant,
sir.
sir.
Okay.
Sir, any question and answers? Is there one is appearing here?
Sir, it is only PPT is not visible on the screen. That
Okay.
question raised by Mr. Kodi Sampath. So it's not related to any subject.
Okay. Right. Well, sir, I think, but Srikant, sir, please vote of thanks to this today seminar.
Okay, sir. Okay. Thank you, sir. Respected dignitaries, esteemed panelists, dear participants, and organizing team members. Good evening to one and all. On behalf of the Institution of Engineers India, Kottagudem Local Center, I feel deeply honored and privileged to deliver the vote of thanks for this insightful and enriching one-day webinar on the application of numerical modeling in mining. First and foremost, I express our heartfelt gratitude to our esteemed panelists for sharing their valuable knowledge and expertise. Sri D. Ramesh, Assistant Manager, R&D Department, Singareni College Companies Limited, Kottagudem. Thank you, sir, for your technical insights and a real-world perspective on the application of numerical modeling in the mining industry. Sri
Thank you,
C.H. Ravikiran, Lecturer, C. University College of Engineering, Kottagudem. Thank you for your academic viewpoint and for helping us understanding the practical integration of modeling technique in engineering education and research. A special thank to our moderator, Sri V. Karnakumar sir, lecturer, Gaut Polytechnic College, Rudrampur, Kottagudem, for effectively guiding the session, ensuring smooth coordination and engaging interaction throughout the webinar. I also express my sincere thanks to Dr. Ram Mohan sir, FIE Chairman, to Kottagudem Local Center for motivating us. We are also thankful to all the participants, students, faculty, and professionals for their interactive involvement and thoughtful questions, which made the session interactive and meaningful. I sincerely thank the Institute of Engineers India headquarters, organizing team, and technical staff who worked behind the scenes to ensure the seamless execution of this program. For your dedication and hard work are truly commendable. Let us take forward the insight gained today and continue exploring innovation in the field of the mining. Thank you once again. Wishing you all continued success and good health. Jai Hind. Hello, sir.
Thank you, sir.
Hello.
Thank you. Yeah,
Thank you.
thank you, Dr. Srikanth, sir. Thank you.
Hello, Karnakumar, sir.
Thank you, sir. I think we are end of this webinar, right? So with the permission of the chair, I will like to end this webinar, thanking you all to the, especially to the Kottagudem Local Center for organizing such an event, and all the panelists, the moderator, and also the participants who has been a patient listener for long hours, for 2 hours, and they also have gained, I think, much knowledge from this contemporary topic, which is very important from the field of mining engineering. I'll thanks again to all the staff of the Kottagudem Local Center for organizing such an event. With this, I am ending the webinar. Thank you all.